Now, when we're talking about sensors themselves and the dynamic range within them, it's important to realize that these sensors can't actually become more sensitive, if that makes sense. So the fact that we have ISO is somewhat, only somewhat of a lie. And that is that these sensors, they pretty much are at maximum sensitivity when you turn them on. But what happens when you increase the ISO is that it's sort of like it's cheating a little bit. So at ISO 100, for example, you are allowed to fill up this entire bucket with light, or with water, if you will. And you read all of this information from that bucket. Now what happens at ISO 200 is that it basically doubles all of the information within a pixel. It doesn't do this in electronics. It's done in an analog way. So it's sort of like it's sort of like turning up the gain on an amplifier, for example, or on an what you're doing is you're not actually making it, in this case, any more sensitive, but you're just making the data that you have matter more, if that makes sense. So what's happening is that you can think of it in terms of doubling all of this information that you have. So just imagine for a moment that for ISO 200, whereas for ISO 100 we were able to fill up this entire bucket, for ISO 200 now, we only fill it up halfway, and we arbitrarily say that filling it up halfway, that's absolute white. That's as bright as it's going to get. Because we can double now all of this information, and things will appear to be twice as bright. Does that make sense? So rather than just having a one-to-one relationship of brightness now, in ISO 200 we can essentially double the brightness of everything, and it's as if it is one stop brighter. Similarly, for ISO 400 we can say, okay, well, I will multiply everything by 4, and now that means that everything is going to be 2 stops brighter. Now, realize that this is only somewhat true, because as you use these smaller capacities for the ISO, you actually get almost for free a decrease in the amount of noise. So it's not as bad as this might look, that every time you're increasing the ISO, you're decreasing it by half. It's actually a little bit less than that. And if we take a look at a lot of the data that exists within this sort of technology, we see that this is actually very close to true. So at ISO 100 and 200, it's very close. But as we start going down, we can see that we're losing a number of stops of dynamic range. And it's almost 1 stop of dynamic range every time we increase the ISO on this digital camera. So this means that to get the best quality, you have to use the lowest ISO that's possible. Now, using or having about 9, 8, even 7 stops of information is passable. That's certainly fine, because compact cameras do it all the time, and it's not that big of a deal. But you're not using all of the quality that's available to your camera. So this is not meant to scare you away from using higher ISOs, of course, because you have to in order to take photos with a reasonable shutter speed or with a reasonably small aperture. But this is just to show you what happens within the digital camera when you do increase the ISO, is that you are losing dynamic range because of the way that the camera is reading the data from the sensor. So as you increase the ISO, it's reading less data. It's considering like this half, for example, to be brightest white. And it's just going to be doubling this information that exists within the sensor. So, and again, it's not a full stop, because other noise levels do decrease while you increase the ISO, but you are losing some of this quality that you used to have. And if you remember, when we're talking about having these smaller buckets, you can see that now that fewer photons are capable of being stored in these smaller buckets, increasing the ISO is even more harmful to a smaller camera than it is to a larger camera. So generally, having the biggest pixel that you possibly can is a very good thing, but we are to the point where that's not the end-all be-all. It is something to pay attention to, but it's not sort of the most important thing to keep in mind. Now, so increasing the ISO can be a dangerous thing to your image quality, but many times you won't even be able to notice the difference in the photos. Having just one stop of difference isn't necessarily going to be as much as you would think when you look at it. Now, when you get to these very high ISOs, around 3200, 6400, that's when you will begin to tell the difference from these ISOs, from these topmost ones, or from the least sensitive ones, and you have to be careful there. But again, this is meant to show you what can happen. Okay, now digital cameras have different types of sensors. So there's two different types. There's two major different types of sensors. There's one called a passive pixel sensor. There's one called an active pixel sensor. And so within active pixel, the major one that we have is a CMOS sensor. And we also have one that Nikon developed for a little bit. I'm not actually sure if they're using it anymore, is the JFET LBcast one. And then within the passive pixel sensor, we have CCD. Now there's actually a big difference between the two. Typically, we see CCD sensors in compact digital cameras, in ones that are not as large, and we see CMOS sensors in larger cameras. And the reason for this disparity is that the CMOS sensors use slightly less energy, but they're also slightly noisier. But remember that these sensors are much larger than their compact camera brothers, so that means that they can get away with using slightly noisier sensors at the expense of having larger or better battery life, because they have these larger sensors. And so that is one of the reasons, though not the only reason, why digital SLRs tend to have better battery life, is that their sensors are more efficient. Now the CCD, on the other hand, even though it's more prevalent, it is less noisy, which is good for compact digital cameras because they're already pretty much as noisy as people can tolerate them to be, but they do occupy, or they do take up, more battery life than your typical CMOS sensor. So again, as with everything else, it's give or take, and most of the time they select to have less noise at the expense of using more of your AA batteries. And one of the things that I think is particularly neat to take a look at is this video that I have of how CCDs are made. And this, I think, will maybe not... You probably won't be able to go home and be able to make your own CCD sensor after this, but I do think that it's an interesting look into how digital cameras are created.
Semiconductor is the image sensor in a digital camera or camcorder. When you snap the shutter or press record, you expose the CCD to patterns of light. It captures them electronically by converting them into millions of electrical charges. The camera's processor then reads these charges and translates them into pictures or movies. CCDs, or charge-coupled devices, are made of silicon, the main element in sand. What's special about silicon? When light hits it, you get electrons. Production begins with a round silicon wafer, 6 inches in diameter, and about as thick as a shirt cardboard. It goes into a steam oven for 3 to 4 hours. The intense heat, along with oxygen and hydrogen gases in the steam, create a glass-like layer on the wafer. This insulates the silicon against the miniature electrical circuitry that will be built on top of it. But first, the wafer is covered in conductive material. This layer measures less than a micron. A human hair is 100 times thicker. Next, a robot applies a 1 micron thick layer of photosensitive resin, which will undergo a chemical reaction when exposed to light. A technician places a mask over the wafer. The pattern on this mask is the schematic for part of the circuitry. When you take a picture, you expose the silicon wafer to light, and that generates electrons. The circuitry carries those electrons to the camera's processor, which reads the charges and translates them into an image. This machine exposes the masked wafer to ultraviolet light. The resin underneath the circuitry pattern remains intact, protecting the conductive layer beneath it. The resin on the areas not masked by the circuitry pattern needs to be removed. Chemicals are sprayed on. This dissolves the resin, exposing the conductive layer underneath. Technicians repeat this entire process with anywhere from 13 to 30 masks until they've built up the full circuitry pattern on the wafer. Next, technicians submerge the wafer in acid, which eats away the uncovered conductive layer. So now, the only conductive material left on the wafer is the actual circuitry. Next step, a thorough rinsing in tap water to remove the residue. Then a rinse with purified water to remove any impurities left by the tap water. Throughout production, contamination is a concern. A single speck of dust can ruin an entire wafer. To protect and insulate the circuitry, the wafer is coated in liquid glass, then baked for 2 hours until the glass hardens. The wafer surface is divided into 25 million tiny square cells called pixels. When you take a photo, each pixel records the light intensity of a minute portion of the scene, generating an electrical charge. A filter on the CCD translates each pixel charge into color. The company makes this filter with 3 pigment powders: red, green, and blue. These 3 colors combined in varying ratios can reproduce any color. The camera's processor reads and then reconstructs the photograph scene pixel by pixel. Each finished CCD undergoes a battery of automated tests to ensure that all the circuits are functional. The machine marks faulty circuits with ink. Just one bad circuit means the entire CCD needs to be discarded. Technicians then check every CCD under a microscope, looking for scratches that might have occurred during the production process. The number of pixels on a CCD varies, depending on what type of camera it's for. This one is a 25 megapixel CCD, meaning it has 25 million pixels. This company even produces a single CCD that has 111 megapixels. So the next time you say cheese, remember that you're producing a digital photo thanks to all that painstaking work that went into the sophisticated CCD semiconductor inside your camera.
Now, one of the things that's interesting about this is that you'll notice that they generate each of these sensors on wafers, and the wafer is a particular size. It's kind of a fixed size, and so if you increase the size of the sensor that you're manufacturing, it takes up more space on this wafer. And generally, one of the things that you noticed on there was that it's actually kind of common for circuits on these wafers to fail. So if you have a larger sensor that's taking up a larger area on this wafer, then it's more likely that that one sensor is going to be faulty during the manufacturing process. And this is just one of the reasons why full-frame sensors are so much more expensive, or these larger sensors are so much more expensive to purchase than these smaller ones. There are, of course, other factors, like generally they give you, better features and better digital camera bodies themselves, but the sensor is a significant portion, or at least a not an insignificant portion of the cost itself. And so remember that with digital photography, size does matter. And even though I'm quick to say that compact cameras, they have their place and they're very good for a certain amount of things, if you want the utmost in quality, you usually have to go bigger. So next time we will continue with this, but don't forget that this Saturday we have National CSE7 Day that John was so kind to organize and host for us. And we will be meeting at, let's see, I have to remind myself, noon this Saturday, the 14th, at the main entrance of the Park Street T-Stop. We'll all get together. I'll be carrying my big thing of camera stuff, and we'll be taking photos, and we'll be able to discuss and talk and do whatever, likely for, depending on not only the weather, but how tired we get, probably for an hour, 2 hours, maybe 3 hours, however long we decide. and I hope to see you all there. And until next time, have a great week.